I'm Rod Steiger. You've seen me in such fine quality chemistry educational videos like acid. Why does it dissolve stuff? And drop that base. Part 3. Okay, we're kind of rounding out our acid base chapter here, and I need to talk a little bit more about bases themselves as we wrap things up. We've spent a lot of time talking about acids. We've talked about pH and pOH and the concentrations, equilibrium concentrations, all that stuff. But now we need to go and talk a little bit about bases. Okay, so we're going to look at bases in general. Okay, and then we're going to move on for the rest of the time. So OH, OH minus is a strong base. Well, what do we mean by strong base? Again, it dissolves very well in water. Because remember, water by itself will break off into H3O plus and OH minus. So, that being said, okay, the hydroxides of the alkali metals, oh wait a minute, what are those alkali metals? Sodium, potassium, cesium, rubidium, those guys, okay, along that first, see these guys right here? These guys right here. These are your alkali metals. Okay? So, they're strong bases because they totally dissociate completely. Okay? Now, on the other hand, you got hydroxides of alkaline earth bases. Well, what's the alkaline earth? Well, it's our beryllium, magnesium, calcium, strontium, barium, and radium. Okay? We have those. They're strong di-basic bases, but again, they're not that great for dissolving in water. But yet we can use hydroxides to an extent as antacids because the OH won't build up in the water because it doesn't dissolve very well. But it does help cancel out the H plus ions in the water. Now, what about those bases that don't have OH minus? I mean, we can think about NH3, ammonia. That's a pretty good example right there. As we're going to let me shift a little bit over this way, and let's focus a little bit more on the topic here. Okay, so bases like those, well, those are proton acceptors. Whereas if you looked at the other definition of base, you could look at it as OH creators. They give off the OH. So NH3 and H2O gets us NH4 plus and the OH minus. Here's your conjugate acid because it took in a proton. Okay, it is the lone pair on the nitrogen itself that accepts the proton, but it does give the overall charge of +1. Now, many of the weak bases out there, and again, when we say weak, we're looking at those bases that don't dissolve very well in the water. Their dissociation is, what, less than 5%. Okay, they contain nitrogen. Very interesting. It's a pattern that we are seeing. So here we represent B for base, aqueous plus water. We get B for base plus that proton and the OH minus. So if we look at the constant, our dissociation constant, or you could look at it as the equilibrium constant, you will notice here that Kb is equal to BH plus multiplied by the OH, so the concentrations of these two divided by the concentration of the B. Now notice I would want to point out, ladies and gentlemen, as I try to see, let me readjust the, here we go, there we are. Yeah, as we readjust, there we go. As we readjust here, remember we don't take the H2O into account when we're looking at our acids and bases. We don't. It's just a non-player. So let's look at the strength of bases for a moment. So hydroxides are strong, the OH minuses. The others are weak. If you have a smaller Kb, okay, then you've got a weaker base. It doesn't dissolve very well in the water. And here we go. Calculate the pH of a solution of 4.0 molar pyridine C5H5N, where the Kb is really, really small. It's just like we did for the acid. Okay, using this same basic formula here. That's all that it is. Okay. Polyprotic acids, I did talk to you guys a little bit about that before. that they'll always dissociate, but stepwise. The first proton comes off, then the second proton comes off, and then maybe the third proton comes off, depending again the kind of acid that it is. But the first step, the first proton that comes off, that equilibrium constant, that dissociation constant, if you will, it is huge, big, compared to the second and the third. And then to pay attention about how it's denoted, Ka1, Ka2, Ka3, that would be kind of important. When we look at polyprotic acids, for example here, this is carbonic acid, which is also found in our blood. It kind of helps stabilize things for us in the blood. Okay, in the first step it becomes a base, and yet in the second step it turns into an acid. Okay, go for it. In calculations, we can typically ignore the second dissociation. Well, wait a minute. Why would we typically ignore that? Because it's too small in comparison to what the first Kb, the Ka is. That's just basically it. So what about salts and acids and bases? Okay. Well, yeah, salts are ionic compounds. Now, when they think about the word salt, people think, oh, it's NaCl. Well, yeah, that's one kind of a salt. It's, when you think about it, my comparison would be if you think about a car. Well, there's different kinds of cars out there. You know, you have the Ford Mustang, you have the Volkswagen Jetta, you have the Chevy Camaro, and you can see where that's going with it. So, here, on the other hand, salts is the same idea. It's the salts are ionic compounds. Okay, typically it's a metal and a non-metal that are connected together. Okay, now the salts are the cation of strong bases and the anion of strong acids. They're considered neutral, like NaCl, for example, KNO3. Those would be examples of that. You don't have equilibrium for strong acids and bases, and typically we're going to ignore the reverse reaction. So we're not worried about the thing going back and forth here. Okay, if we look at basic salts, so if you have the anion of the salt is the conjugate base of a weak acid, you have a basic solution. So in an aqueous solution of sodium fluoride, okay, for example, the major species of that would be sodium, chlorine, and water. Because you have fluorine plus the water, it would go back and forth where you get HF plus OH minus. That's basically it. So here, when you look at the Kb, okay, if you look at it as a base, all right, in this case here, you see where everything is put together, our normal equilibrium thing. But if you look at Ka, on the other hand, you got, because when you look at this here, okay, Ka, you are also going to have this as well. So it seems to be a little bit confusing, but hold on. If we were to go and look at Ka and Kb, the equilibrium constants of the acids and the bases, which if we look at the previous thing, it's totally legitimate given what we have here. Okay, so we can look at this from a base point of view and from an acid point of view. That's what we're looking at. So if we look at Ka times Kb, which is what we have here, which we brought over from our previous slide, we bring that into here, Ka times Kb, you're going to find something. You're going to find that there's some cancellation, isn't there? Notice how the HFs will cancel each other out. Okay, as will the Fs. They also will cancel each other out. So what do you have at the end of it? Ka times Kb is equal to the hydroxide concentration times the hydrogen concentration, or Ka times Kb equals the dissociation constant for water. Oh, yeah, water. That's just it. Ka, yes, will tell us the Kb. The dissociation constant for the acid will also tell us the dissociation constant for the base. When we are looking at something, the anion of a weak acid is a weak base, so there's a connection here, okay? And again, calculate the pH of a solution of 1 molar NaCN. The Ka of HCN is 6.2 times 10 to the minus 10, okay? We've done this before. Okay, the Cn minus ion, this is cyanide for those people who are wondering, competes with the OH minus for the hydrogen ions there. Yeah. So, what about acidic salts? So a salt that has the cation of a weak base and the anion of a strong acid is going to be basic. Yeah, it's going to be a basic. So again, the same development as the bases, you're going to get the same thing. Ka times Kb equals Kw. So then here in this case, calculate pH of a solution of 0.4 molar NH4Cl. The Kb of NH3 is 1.8 times 10 to the minus 5. Again, we've done this before. Other acidic salts are those of highly charged metal ions. Okay? So anion of a weak acid, cation of a weak base. So if the Ka is greater than Kb, it'll be acidic. If Kb is greater than Ka, it's going to be basic. If they're equal to each other, then guess what? They're neutral. This is not really a big surprise. This is kind of intuitive. Okay. So let's take a look at the structure and acid-base properties. If you've got a molecule that's got an H in it, it's a possibility that it's a potential acid. Maybe, maybe not. There's some other things to look at. The stronger the XH bond, now what is that X? That X can represent any other part of the molecule that's there. It can represent any part of the molecule, the less acidic. The stronger that hydrogen is bonded to the rest of the molecule, the less acidic. Compare bond dissociation energies. So stop and think about it for a moment. This statement, it makes sense. Here's why. Because the idea behind an acid is you're basically giving off a proton. You're a proton donor. Okay? If you look at it that way. If you have a stronger bond that's there, then it's less likely to be an acid. It's less acidic. Now, the more polar the XH bond is, then the stronger the acid is going to be. And that's where you get to use electronegativity, use the electronegativity chart. But if you stop and think about it, when you look at electronegativity, here's a review. Here's hydrogen over here. And over here, these guys are 0 because there's no interest in adding electrons. But these guys, it's going to be pretty strong, right? Fluorine is pretty strong for that. Chlorine is pretty respectable. And then here's hydrogen. So when they're on opposite ends like that, they tend to be more polar covalent or ionic. Okay? The closer that they tend to be more non-polar covalent. Okay? Ionic, it's extremes. Okay? Polar covalent can also be extremes, but not as much. You can make the argument that an ionic bond is a polar covalent extreme. Kind of like extreme sports, for example. Okay? Let's move on here. So, the more polar the HOX bond is, you've got the stronger acid in there. So let's take a look here for a moment for oxyacids, strength of oxyacids. Well, what are oxyacids? Those are acids that have oxygen in them, okay? If you've got more oxygen hooked into the central atom, yep, the more acidic that hydrogen is going to be. So if we look at it here, you've got 4 oxygens. The central atom will be chlorine, 4 oxygen atoms. Here's your hydrogen. It's going to be more acidic than this hydrogen over here. Why? Because it's got more oxygen atoms. Okay? The H is attached to an oxygen atom. That's the thing. It's not hooked up to the central atom, but it's hooked up to one of the oxygen atoms. So the oxygen atoms, of course, they are electronegative. They're certainly more electronegative. If you look at the position, they're certainly more electronegative than the hydrogen is here on the opposite end. So what happens about electronegativity? It wants to pull electrons to itself. The more electronegative that the atom is, the more it wants to pull to itself. Okay? So it will pull electrons away from the hydrogen. If it pulls electrons away from the hydrogen, that makes the hydrogen even more of a plus. It makes it even more positive. Okay? So, Let's look at strengths of oxyacids for a moment. Here's an example. If you think about electron density here, you're going to have more electron density toward this end, which would make sense because chlorine loves electrons, oxygen less so, and hydrogen, hydrogen's like a little kid. You can take away the electron very easily with that. So again, if you look at electron density, you can see how it's just pulling even more. The electrons are, when we say electron density, remember, the idea is about probability that you're going to find the electrons there. And guess what? Compared to the first slide here, where you have one oxygen atom connected to our chlorine, in the second one, you've now got two oxygen atoms connected to the chlorine, and guess what? They're going to pull the electrons away. They're going to make this even more positive. They're even going to make it more radical, if you will. Here's, if you're putting in a third one, what's happening? Here you go. Oh my gosh, you're making this even more. Okay, because now the electron density is more going this way. And then when we go here for our last one, okay, HClO4, well, the H is connected to this one lone oxygen, but you've got all these other oxygen atoms. They're pulling those electrons out and make the hydrogen even more intense. Whew. Yeah, and we keep seeing this over and over again in nature. Okay, my time is running out. Hydrated metals, okay, so here's the thing. Highly charged metal ions pull the electrons off of surrounding water molecules toward them, and it makes it easier for the H's to come off. Okay, if you stop and think about it, aluminum comes in, highly charged, rips electrons off the oxygen. Now the hydrogen is ready to go because it doesn't have the same amount of electrons holding it in when we talk about hydrated metals. Acid-base properties of oxides, so yeah, non-metal oxides, okay, dissolve in water can make acids. So here we have an SO3 plus H2O, and we can get H2SO4, sulfuric acid. Okay, so ionic oxides dissolve in water to produce bases. So here's when you look at non-metal oxides and ionic oxides. Now remember, ionic, think about the electronegativity table like CaO. For example, in water, you get CaOH2. So this is a base. Well, wait a minute, what's going on here? Here's your clue that it's a base when you see that OH. That's there. All right, got to move on. Lewis, acids and bases. This is Lewis, the guy who came up with the electron dot diagram. He looks at it differently. He doesn't look in terms of protons like Bronsted-Lowry and Arrhenius did. He looks at it from a perspective of electron pairs. You know, those funny little dots. So acids are electron pair acceptors and bases are electron pair donors. That's how he looks at it. Okay, so if bases are, so for example, here's an NH3, it would be a base, okay? It donates its electrons to the boron trifluoride because the boron trifluoride wants more electrons. And that's the way when you look at a Lewis base here, because it is donating its electron pair. Okay, this is the basic definition here. So when you look at boron trifluoride, it wants more electrons. The BF3 is a Lewis base, whereas the NH3 is a Lewis acid. Okay, that's what you have to look at. So acids are electron pair acceptors, bases are electron pair donors. Okay, so we look at this, that BF3, according to Lewis, it would be a base. It's a Lewis base compared to a Lewis acid when you combine these together. Okay, and when you go ahead and you look at something like this at the end here, all right, so here's water connected with the aluminum, and you can see that it gives up one of its electron pairs to the aluminum. Guys, that's it. We're going to stop here. I hope this helps out a little bit. Till then, the next time. Hasta